Now take an arbitrary Fourier component of a vector perturbation. We have seen that we can divide vector perturbation into longitudinal component S and transverse component V. So there are three components in Cartesian space, three components for each vector. And now I will demonstrate that these components do not mix. That is, S components do not mix with the V components in the Fourier space. How we can see this? In order to see that, let us align the z-axis parallel to vector k. And when you do that, you will see that for vector S, which is a longitudinal part, there is no x and y component. For the vector V, which is the transverse part, there is no z component. So you see that when I write this vector perturbation by adding these two components, I will get V1, V2 minus Is, because I will get x and y component of the transverse part and the z component of this longitudinal part. So these components, transverse components, they live in the plane which is perpendicular to vector k, and the longitudinal component is parallel to k. So this is what we are going to see. This is what this means, and it's not difficult to derive this, and that's what we are going to do now. We are going to see that how, after taking z-axis parallel to k, we can clearly see this division. It's not that we have to do z-axis parallel to k, we have to keep z-axis parallel to k in order to see this division. They live in their separate spaces. Longitudinal component and transverse component in Fourier space do not mix with each other. But in order to see that, in order to appreciate that, what we are going to do is we are going to keep z-axis parallel to k, and then you can see when we do z-axis parallel to k, you can see that now k is aligned parallel to z-axis, and the longitudinal vector is parallel to k, because the longitudinal vector has only one component, z component, that is the longitudinal vector is parallel to k, and v vector is having only x and y components. So v is in the plane, in the transverse plane, that's longitudinal, which means along the wave vector, and v is the transverse plane, it's in the transverse plane, and it is transverse plane if wave is along the z-axis, then the transverse plane is xy. So v has components only in the xy plane, and proof of this is very straightforward. Just go through all this mathematics, it's very straightforward. I can quickly walk you through this. So we have seen this equation before in the last video, but now we are going to write k is equal to kx3. x3 means z-axis. So you can write ki 0 k, and straightforward mathematics, you can see that I now can write si, simple mathematics, becomes 0 minus is. Nothing fancy, just plain mathematics. Now for the transverse part, we know that its divergence is 0. Now del dot v in vector space, del dot v in vector space becomes ki vi or k dot v, and this is how you can write, how you can come to this. Del dot v in vector in the Fourier space, in the Fourier space is ki vi or k dot v. So how, these are the steps. Again, plain mathematics, nothing fancy. We just write del dot v, plug the Fourier expansion of v, and then just apply the divergence to this. So write this del vector as del over del x1 x unit vector plus del over del x2 x2 unit vector plus del over del x3, x3, all those plain vector calculus. Just apply the divergence here. You come to this step, and then from here you see k1 comes forward. From here k2 comes, I k1 comes forward. Here I k2 comes forward. Here I k3 comes forward. You come to this, and then what is k1 v1 k2 v2 k3 v3? They are ki vi, ki vi. So again, this is KIVI. Repeating indexes, use sum over repeating indices. That's why we are writing this as KIVI. KIVI means K1V1 plus K2V2 plus K3V3 because you sum over repeated indices. And also, you can write this as K dot V. That's what this is. X components multiply together, Y components multiply together, Z components multiply together. That's K dot V. So in the Fourier space, we get del dot V is equal to KIVI is equal to K dot V. Now, I proved this in general. It holds whether K is aligned along Z axis or not. For any general vector V, del dot V can be written as KIVI K dot V. But now in our case, okay, in our case, first thing is that we have K dot V is equal to 0. So when we write K dot V is equal to 0, because the transverse component is divergence free and del dot V is 0. Del dot V 0 means KIVI is equal to K dot V 0. Now K dot V 0 means that what do we have here? K dot V 0 means that this is 0. K1 V1 plus K2 V2 plus K3 V3 is 0. And K1 in our case, K1 is already 0, K2 is already 0, but now it means K3 V3 is 0. So K3 is K in our case. So K V3 is 0. So K V3 0 means V3 is 0 and V vector can be written as V1 V2 0. So you see that the vector perturbation, when you add 2, you can see that the transverse component is in the transverse plane, xy plane, and the longitudinal component S is along the wave vector K, Z axis.